Welcome everyone to session 5. This session is about Epoch of Reionization, cosmic dawn, and clusters. So it promises to be an exciting session. We start with 2 talks about HERA. The first of those talks is by Nicholas Kern, who will present the first results from HERA Phase 1, improved power spectrum limits at a Redshift 8. Remember that questions can be asked on Slack, and Nicholas, go ahead and share your screen.
All right.
Yeah, all set. Go ahead.
All right. I guess I'll start then. Wonderful. Thanks, André. Thanks to the organizing committee. It's a pleasure to be here virtually to discuss some of the recent results from HERA. I'll start by giving just a brief recap of 21 centimeter. I'll discuss some of the HERA limits, some of the interesting bits of the analysis pipeline, and I'll finish with a brief overview of the theoretical interpretation paper that we've worked on. Okay, so just as a brief recap of 21 centimeter cosmology, right? This is a description of the evolution of the universe, and I've highlighted a couple of the ways in which we've learned about cosmological structure in the universe, highlighting the CMB at high redshift, telling us something about the geometry, the content, and the initial conditions of the universe, and some of the spectroscopic galaxy surveys and photometric surveys at low redshift, revealing the clustering of dark matter and the accelerating expansion of the universe, and as well as using the Lyman alpha forest at slightly higher redshifts. But one thing you'll notice is that we don't have a lot of great systematic probes of cosmological structure throughout a broad range of cosmic time. And this is one of the ways in which we hope to use the 21 centimeter line from neutral hydrogen as a probe of cosmological structure. And this is one of its key advantages, which is that it has an unparalleled redshift range in its ability to probe structure. So at low redshifts, we're looking at 21 centimeter from galaxies. At high redshifts, at the Reionization epoch and before that, we're probing the intergalactic medium directly with neutral hydrogen. And of course, in today's session, we'll be talking about using a 21 centimeter line as a cosmological probe of the cosmic dawn and the Epoch of Reionization, which mark the formation of the first luminous structures, the first stars, galaxies, and black holes, and the way in which their radiative feedback influenced the intergalactic medium around them, culminating in the reionization of neutral hydrogen at the EOR. One of the key properties of the 21 centimeter line, being a spectral transition, is that we can use the frequency axis to probe the line of sight. And that allows us to make 3-dimensional maps of the 21 centimeter line, probing the inhomogeneities of the IgM and its density and temperature and ionization state. And that might look something like this. This is a slice through a simulation. And one of the first things we'd like to do is to relate this to some summary statistic, like the power spectrum of the fluctuations. And we're going to use that to constrain some of the physical properties of the first galaxies, the first stars, and of the IgM. And so that's the ultimate goal, at least for now, of early 21 centimeter experiments. And as a consequence, there are a lot of experiments that are trying to do this. Here is a couple of experiments that are currently operating. And these are all experiments that have set some kind of limit on the 21 centimeter power spectrum at cosmic dawn. And today, as I mentioned, I'm going to be focusing on the HERA experiment, and I'll tell you some of the recent results that we've made in analyzing early data. But before I do that, I'm going to give you a sense for what the state of the field currently is right now. So this is a plot showing current upper limits on the power spectrum, limits that have been set over the past 5-10 years. So each point is a limit, not a detection of the power spectrum, but an upper limit on the power spectrum from a variety of different experiments that are shown on the right here. And you can see a couple of key features. So one is over the past 5-10 years, we've increasingly set more stringent upper limits on the power spectrum. So we've been bringing the sensitivity of these experiments, we've been bringing these limits down. The other thing to notice is that in the black lines here, these are some of the fiducial models of the power spectrum. And you'll notice that we're still a couple of orders of magnitude away in reaching those fiducial amplitudes. And that has large part due to the difficulty in actually making this measurement, which I'm sure is going to be talked about a lot during this conference. And And it turns out a lot of these limits are systematic limited. And I'll refer you to a kind of a summary paper that a couple of people, including myself, put out recently, describing some of the improvements that have been made in these existing limits and how they were done. But one of the things that we hope will get us those last couple orders of magnitude is a new experiment that we're building called HERA, the Hydrogen Epoch of Reionization Array. And this is a graphic that Josh put together showing an actual satellite image of the array as it stood earlier in this year. So HERA is going to be a compact radio interferometer in the desert of South Africa. This is showing an actual image of the array. And so you can see that the full core of the array has been constructed, at least the dishes. We're still working on actually raising all of the feeds. But when it's finished, it'll be an array of 350 dish antennas. Each dish will be 14 meters in diameter. And it will observe from 50 to 250 megahertz, giving us access to redshifts of 5 to roughly 25. And there's a couple of photos here showing the site crew assembling some feeds, the science crew on the bottom right, and a close-up of what the dish actually looks like in the field. And this is actually an outrigger dish. So it's going to be 320 dishes in a compact configuration and 30 in an outrigger state, which will give us some improved leverage for imaging capabilities. But what I'm going to be talking about today is data we took very early on in construction, and we call this phase 1. This was data that we took when the array was about this large, just this lower left-hand corner of the array. We were actively building the array during this year. We had about 50-ish antennas, roughly 40 functional. And this is with the old front-end system, which we call phase 1. And that means that we had access to 100 to 200 megahertz observing bandwidth here. And what we did with this data when we took it in 2017 is we really honed in on this phase 1 data set, and we used it as a test bed to develop a calibration pipeline for HERA that's going to serve us in the future going forward. And this is a highlight of some of the work that's been put out by HERA Collaboration members over the past couple of years working with this phase 1 data set. So I won't go into a lot of these things in detail, but we've looked at how to calibrate HERA, model the beam, how to deal with instrumental systematics, both from a empirical data-driven perspective, but also from a more simulating electromagnetic simulation perspective. Even though HERA is not optimized for foreground modeling, we have looked at how to model foregrounds, both from an imaging and a more statistical perspective. And one of the things I'll come back to, which has been a big focus for HERA over the past couple of years, is validation. So constructing a validation pipeline to try to understand our analysis pipeline in finer detail. And this has been a big effort and an ongoing effort currently within the collaboration. But what we did recently was to take a lot of this work and synthesize it into a first limit on the EOR power spectrum with this phase 1 data set, which came out earlier this year, as well as a theoretical interpretation of those upper limits that came out more recently. Okay, so I'll just delve into this phase 1 data set. So HERA, as you may have seen, is fixed to the ground. It does not point, and it does not beamform. So what that means is, as a function of local observing hour, it just scans a constant stripe of declination across the sky. So for the time of year that we were observing and the data set that we looked at, the 18 stable observing nights that we looked for this particular analysis, the part of the sky that HERA saw is shown by this solid box, the solid white box here. But it turns out we went even further and we took little snippets of that data set where there was the least amount of foreground contamination. And that defines these 3 fields, as it were, shown here. And they avoid some of the most pernicious foreground sources like Fornax A and the galactic plane. So that's the basis for this data set. Looking at the frequency axis, as I mentioned, we have 100 megahertz from 100 to 200 megahertz. And what I'm showing you here is the relative flagging occupancy of our data after our RFI flagger. And you can see that there are a number of clear bands that are contaminated by RFI, in particular this wide band here at 137 megahertz from Orbcom. But there are these 2 fairly clean bands, largely clean, and we used those to set the first limits. So there are 2 subbands that we use to form the power spectrum, and that corresponds to redshifts of 10.4 and 7.9. So we've got 3 fields and 2 redshifts. And one of the things I'll highlight about the analysis pipeline that I won't go into too much detail, I could spend a whole talk on these things, but is HERA's approach to understanding the instrument and foregrounds. And unlike some of the other experiments that have set limits like LOFAR and the MWA, which are actively trying, at least in some capacity, to model the foregrounds and subtract them, that's not really the approach that HERA is taking. Instead, HERA is built upon a principle of foreground containment or foreground avoidance, but foreground containment is actually kind of a better way to think about it. And the idea here is we think that foregrounds are intrinsically smooth and are confined to low Fourier modes. And we've built an instrument that tries to maintain that compactness in Fourier space. And we've built an analysis pipeline that tries to maintain that as well. And so a demonstration of this is through our systematics modeling pipeline. So what I'm showing you here is power spectrum from phase 1. And you're seeing it as a function of observing time. And again, because HERA is a drift scan array, local observing time is really just a proxy for right ascension. And so you can carve out these different fields that we're looking at on the sky here. The left panel is showing you the power spectrum before we apply our systematics modeling software, and the right is after we've applied it and tried to subtract these systematics. And so you're seeing a couple of things. A, there are clear contaminating systematics in phase 1 data, and we spent some time trying to understand what they are, and we think that they're effectively a form of instrumental coupling. And so the tailored Fourier filters that we've developed for the systematic seem to do a pretty good job. So they clean up a lot of this high delay, high Fourier mode structure. But they also do something else, which is they make the transition from the foregrounds to the noise a little sharper. And that actually is because it turns out in the process of filtering off systematics, we've also filtered off some of the diffuse emission, which is coming from the horizon. And that's what tends to produce a lot of that foreground leakage here. So it served two nice purposes in making this transition sharper and filtering off some of these high delay structure. And that's kind of the principle behind our foreground containment strategy. Now, before I move on, I'll note one last thing, which is the strength of the foreground power at the 0 Fourier mode is something of a proxy for how bright the foregrounds are in that field. And so you can see, looking at field 1, that it has significantly lower overall foreground emission than the other fields. And if you think back to the map I showed, that's effectively because it's looking at the coldest part of the sky. But that kind of bit of information will serve us when we look at what the power spectra actually look like. Okay, so now I can take the power spectra and I can bin them into a cylindrical power spectrum. So this is showing you the power spectrum as a function of K parallel in the vertical axis and K perpendicular on the horizontal axis. I'm showing you each column are the different fields that we've looked at on the sky. The top is showing the measured power spectrum in logarithmic units. And the bottom is showing the ratio of the measured power with the thermal noise power spectrum, or the amplitude of the power spectrum if they were thermal noise dominated. And so there's a couple of interesting features. So one is we're clearly detecting the very strong foreground emission at low K parallel here. That's shown by this red. But if you look at higher line of sight modes, higher K parallel modes, you'll see that largely the data look roughly consistent with noise. And I've put an asterisk here because quantifying noise can be actually a somewhat subtle process, and we've taken pains to do that in the paper. But largely what you want to see if you're looking for thermal noise are fluctuations that have roughly unit variance and are fluctuating between blue and red in this bottom plot. And so you can see some interesting structure. You see some interesting baseline dependent leakage here for field 2. But by and large, particularly at very high line of sight modes, you're seeing agreement with the thermal noise floor. And that's a good thing, at least at the levels that we're looking at right now, is telling us something about the performance of our analysis pipeline. And said another way, I can bin the power spectra onto a 1D basis. I can bin them spherically. And before I actually show you the power spectrum in normal units, what I've done is I've shown them in peak normalized units. So I'm normalizing by the peak amplitude that's detected that's due to the foreground power at the 0th delay mode, 0th Fourier mode. So what is this telling us? Well, what you're seeing here is that, yes, we detect these foregrounds at very high dynamic range, and it bottoms out to a noise floor at about 1 part in 10 to the 9 in power. And so this is telling us something about the entire measurement process of our system, both the instrument itself and the analysis pipeline that we've applied to the data, that it is containing foreground power in these low Fourier modes to 1 part in 10 to the 9. And of course, we need to do better than that to detect the signal, but this is giving us a spec on the performance of our system. And it's hard to know where this stands with other experiments, because this is not an often way in which we describe our analysis pipeline, but I would encourage people to look at these plots, because it's very informative about the instrument and the analysis pipeline. Okay, so going forward, I can just show you what the power spectra look like. So I'm showing you the fully spherically averaged power spectra. This is for the high frequency band, or the Redshift 8 limits for each field. The pink points are the measurements, and then the black dashed line is our thermal noise prediction. So what we would expect the points to look like if they were due to thermal noise. We would expect them to fluctuate around that level. And so you see a couple of interesting things. So one, for the most part, the data look, like we saw before, roughly consistent with noise, particularly at the higher K modes. Now, there's some indication for deviations from that, and we spent some time trying to understand how significant those deviations. But in particular, for field 2, you can see much stronger deviation from that. And indeed, it looks like we're detecting some systematic, even at very high K. And a couple of other things. If you look at the lower Fourier modes, you can see this kind of tail, and that's coming from the foreground emission that's kind of being killed off. And you're seeing that this tail, it looks different between the different fields. And this goes back to the fact that field 3 saw much stronger overall foreground levels. And so that tail is now being raised up out of the noise floor. Whereas in the field 1, that tail might exist, but it's just a lot lower, and that leads to more sensitive limits. Kind of straightforward. But I will say, by and large, for field 1, which is where we're getting the best limit on the power spectrum, these points above a K of 0.4 are roughly consistent with thermal noise. And we've done some statistical tests to show that. It turns out the points below a K of 0.4 are beginning to show marginal evidence for detection of a residual systematic, but it's at a very marginal level. There's not much we can say, because this is the most average that we can go with the data. What that indicates, as Josh will talk about later, is that we can get more out of our data. And so what we're working on now is actually pushing this further. And I'll let Josh tell us more about that. But it turns out, so that best limit is coming from field 1, both for the low and the high band. And this is where those limits fit in with existing limits. So I'm showing you the HERA limits in pink. Turns out the Redshift 10 limits are roughly consistent with existing low-FAR limits. But the Redshift 8 limits show a significant improvement over existing limits by over an order of magnitude. Now, again, we're still a couple of orders of magnitude away from those interesting fiducial models, but this is a significant improvement. And it stands to ask, well, what is that telling us about the IGM at these redshifts? But before I go into the interpretation, I want to highlight briefly some of the work that I mentioned before on the development of our validation pipeline. And this has been really a collaboration-wide effort that's been a lot of people have contributed to, but in particular, I want to highlight a couple of people that have really been at the fore of this effort down below here. And this is showing you a schematic, a broad schematic of the validation pipeline. So what we do is we have a number of different models for the EOR signal. We have a number of different models for the foregrounds. We have beam models, array layouts. We push that from the sky down to a measurement of the visibilities, and we have a couple of different simulators in order to do that. We inject a number of realistic instrumental systematics into the data, and then we push that through our analysis pipeline. And then furthermore, our power spectrum pipeline, and we look at the final result. And what we're trying to understand is if the pipeline that we have gives us the answer that we know we put in. And that's effectively trying to understand if our pipeline is unbiased. And I'll cut to the chase on one of the tests that we've done with this, one of the interesting tests, and that is to understand if we recover a fiducial EOR signal that we've injected into the data at the appropriate amplitude. So what I'm showing you here are some of these mock validation simulations that we've pushed through the analysis pipeline and then formed their power spectrum. This has foregrounds, it has an EOR signal, and it has noise. And that noise you're seeing here is this noise floor at high K, and the noise floor is indicated by this dashed line. And what we want to show is that when we form power spectrum from our data and then we begin to average those power spectra together to integrate down the noise floor, we want to show that we can recover a known signal in the data. And so that's what you're seeing here is as we continue to integrate more and more of that data, the noise floor decreases. And when that noise floor goes below the input EOR signal at the given K modes, we see a detection of those signals. That signal rises up out of the noise floor at a non-negligible SNR. So that's the gist of the analysis here. And there's a lot of other ways in which we try to assess the performance of the pipeline. I will say one of the other things that we learned in doing this, one of the major things is that there was roughly a 7% bias in the way in which we set the absolute flux scale of our data. So we were able to probe our analysis at roughly the 7–10% level, and we were able to correct for that after the fact. So this is showing you after having corrected that, what this looks like. Okay, and as I said, that's an ongoing process that we're improving for future analysis as well. Okay, so in the last couple minutes here, I'll move to discussion of a more recent paper, which looked at interpretation of these limits. And like the limit paper, this interpretation paper was multi-tiered, and it was the effort of a lot of people. And in particular, some of the people that I've listed here led some of the sub-analysis you can find in the paper. Now, I'm not going to talk about all of the results here. I'm not even going to talk about all of the different ways in which that paper looks at modeling the signal. I'm going to talk about one specific way, one tool that we use, in particular using 21CM fast and some of the results we're getting from that model. And I'll let Julian a little later on in the session talk about some of the constraints on dark matter. But please see the paper if you're interested about these various ways of modeling the data. I will say just up front that all of these different ways of modeling the signal roughly agree. And so that's kind of a reassuring statement that we have different ways of modeling the signal and we have rough agreement with constraints on IGM physics. So as I said, we're not in the territory of ruling out fiducial models. We're more about ruling out very exotic extreme models. And one of the kinds of models that we're beginning to rule out are these cold IGM models. And so before I show you these limits, I'll first describe what that means. So I'm showing you an evolution of a couple of different temperatures in the universe, from early times on the right to late times on the left. So the first thing you're seeing is the CMB temperature in blue, which falls off like the scale factor. You're also seeing the gas temperature, which at redshift 200 decouples from the photon field and then begins to cool adiabatically. So it's cooling faster than the CMB. At some point, we think the first sources of X-ray emission turned on. They injected X-rays into the IGM and they heated it up. So that causes the gas temperature to skyrocket and exceed the CMB temperature below a redshift of 20. There's also the spin temperature of the 21 centimeter field of neutral hydrogen. It has a much more complex evolution, but at the redshift that we're interested in, below a redshift of roughly 10 and below, we're going to assume that it's coupled to the gas temperature, which is a fairly safe assumption. So we're going to use the spin temperature as a proxy for the gas temperature here. But one of the things that could have happened is that when these first X-ray sources were formed, they may have been inefficient in actually heating the gas. Whether that's due to the exact shape of their SEDs or the fact that they formed a little late, or their overall efficiencies, they may have not really heated the gas. And so you may have seen a gas temperature that looked something like this, that remained very low, even down to redshifts of 10 and 8, the redshift that we're probing with HERA. Okay, so if you can include these models in, say, 21CM fast, a cosmological semi-numerical simulation, and you can survey the parameter space and try to set constraints on properties of the IGM. And in particular, one of the things that we're constraining is the average spin temperature of the universe at redshift 8.
You have 2 minutes left, Nicholas.
Oh, yeah, thank you. So, and yeah, in the last 2 minutes here, I'll just summarize these constraints. So this is showing you the average constraint on the spin temperature. In gray, you're seeing the prior that was explored by the model, which is a very broad prior. You can see it has a lot of models that have low spin temperature. The gray shaded is showing you that adiabatic cooling limit. So in fiducial models, the gas can't get cooler than this. And so that's why you see these models kind of get, that they peter off below this. In orange, what you're seeing is constraints on the average spin temperature with existing constraints on this quantity, namely from Hubble UV luminosity functions, quasar spectra, and the CMB optical depth. But what you find is as soon as you include the HERA limits, you see a strong preference for hotter spin temperatures. And you see a lot of the models that have low spin temperature, near adiabatic spin temperatures, they're effectively ruled out. So at 95% confidence, the HERA limits favor a heated gas temperature above roughly 2 Kelvin. And you can see that here too. So this is another way of showing the evolution of the spin temperature as a function of redshift. Again, that gray line is that adiabatic cooling limit. And at redshift H, shown by this purple arrow here, HERA is ruling out adiabatic, pure adiabatic temperature. So there has to be some kind of heating in the universe by redshift 8. Another way to say that is that the X-rays, the sources of X-rays must have been at least somewhat efficient in heating the gas. And so you can turn that into a constraint on the overall X-ray efficiency of the first X-ray sources. And what you're seeing in orange is existing constraints on the overall X-ray efficiency of these sources. And when you include HERA limits, you see a strong preference for more efficient X-ray sources. And the solid line is showing you, say, a high mass X-ray binary in the local universe. The dashed line is showing you a population of low metallicity high mass X-ray binaries, which have more efficient luminosities. And so you're showing that HERA is, interestingly, favoring a population of X-ray sources that don't look like their local analogs, which is entirely expected, but this is one of the strongest constraints on these properties at this redshift. Okay, so with that, I'll leave you with my summary slide, which is that hydrogen is a very powerful theoretical probe of cosmological structure from present day all the way down to the first stars. There are still a number of significant challenges that stand in the way of its maturity to a true cosmological probe, but progress is making fast. It's being made fast, and as I've shown, the HERA experiment is already setting new limits, even with a fraction of the array, a fraction of an observing season, that's yielding new constraints on the IGM. So thank you for your time. I'm happy to answer any questions.
Great, Nick. Thanks. Great talk. If there are any questions, please raise your hand using the reactions. I don't see immediately any questions. Well, I can ask something. Well, let's start with a very generic question. And do you think that HERA can make a detection of the EOR signal?
Yeah, that's a tough question. I'm optimistic that it can, but I'm realistic about the challenges that stand in the way. It's not going to be easy, and it's going to take a lot of person power and time. And we have shown the ability to understand the system at a very fine level, to 1 part in 10 to the 9. So we need that extra 2 to 3 orders of magnitude, but of course those are the hardest. So I'm optimistic, but also realistic. Yeah, I hope so.
Great. Joe?
I just had a super quick and general question, Nick. How did you do the flux density calibration, your absolute flux density calibration, when you're such restricted in the field of view? I was just wondering if you give that. You alluded to it, but it's super quick.
No, yeah. So roughly, we use the MWA Gleam catalog, which has been a huge aid in calibrating HERA and understanding the system. It's great because they are at roughly the same latitude. So we use a point source catalog effectively, and we do kind of some tricks to try to mitigate things like diffuse emission, and then like really strong extended sources like 4NXA. So we use restricted fields of view, and then we use a certain set of baselines to calibrate, but it's tied to the MWA Gleam catalog. Yeah.
Cool. Yeah, I really need to write a paper to show. Yeah, the flux scale is a bit high, 3%. But anyway, I think you got other systematics to worry about than a 3%.
Okay. Yeah. Last question by Lincoln Greenhill. Go ahead, Lincoln. You're still muted.
Sorry about that. Nick, that was an outstanding talk. Thank you very much. And at the EOR frequencies, my interpretation of, for instance, just the K-perp and K-parallel axes is that HERA is basically acting as an interferometric spectrometer. And that will be exaggerated when you go to much lower frequencies with the goal of getting to redshifts of 20 or so. And just having the feeds go that far doesn't necessarily guarantee success. So given your, I guess, relatively conservative answer a moment ago to will you be able to make the measurement, what is the prognosis for cosmic dawn?
Yeah, it's a great question. So, performance in the mid band does not guarantee performance in the low band, right? That's exactly, yeah. What I will say is that HERA is optimized for the wideband. Now, of course, you can't optimize the entire band at once, so there are some compromises. We are actively working on phase 2 data, so low band data, I hope at a future date we'll be able to talk more about that. We're still very much working on commissioning the experiment in the low band. There are more challenges in the low band as well. What I'll say is, I'm optimistic that we can make a low band detection, but even if we don't, there's so much open parameter space in the low band that even very stringent upper limits is going to tell us a lot about the universe at these times. So I'll leave it at that. Yeah.
Great. Thanks, Nick. Let's leave it at that indeed. But if you have further questions, refer to Slack. And then our next speaker is Josh Dillon, who will continue talking about HERA and answer the question, what's next for HERA? Go ahead.
Yeah, so this perfectly dovetails from Lincoln's question, so I promise that wasn't the plan. And I want to thank the organizers and Nick in particular, who really set this up quite well and did some really pioneering work on the phase 1 limits that we have so far. So to start off more or less where Nick left off, HERA has set the deepest upper limits on the 21 centimeter power spectrum to date. So that's an accomplishment, but it's not something that we're not resting on our laurels. And the real question that we're actively trying to answer is, how do we go deeper? And there's a couple of approaches to that, of course. One is just to use more data. So the amount of data that Nick was looking at and that all of us were looking at during this first analysis was 18 nights of data. But from that same season, the full season of HERA Phase 1, we have well over 100 nights. And while after a variety of cuts, it's a similar number of antennas per night, it's still a significant increase in the potential sensitivity just from that raw extra data. So I took the analysis pipeline we used with some modifications and processed it through all these various analysis steps and created various Jupyter notebooks that let us look at how the analysis is performing at each step at each night. And then by hand inspected something like 500 Jupyter notebooks to end up with 94 good nights of data. So the amount of sort of nights per LST bin is going up by a factor of 3, almost a factor of 4 in this larger data set where we call them internal data release 1 and 2. But the point is that it's the full season of data where we're seeing a much wider range of LSTs and we're going much deeper. So in general, we're trying to apply more or less the exact same analysis that we've really battle tested and validated with simulations to the data that we want to look at here. And one of the most important things, which Nick touched on, I'm going to go into a little more depth on, is this rejection of these cross-coupling systematics. So these systematics here and here, which are very successfully rejected, so this is before and after cross-coupling subtraction, these are appearing on virtually every baseline and are a major systematic for our result. And the way that Nick actually was able to reject these is to look at, instead of just looking at the Fourier transform along the frequency axis, looking at the Fourier transform along both the time and frequency axis. So this is the fringe rate delay space for those not used to looking at that. And the sky signal should occupy this block here, which is a baseline dependent fringe rate. But the cross coupling occupies fringe rate 0. And so by filtering out that fringe rate 0 mode, basically throwing out all of this up here and keeping everything else, we're substantially reducing the systematics. Now, that didn't actually work quite as well in a full season of data. So when we made these sorts of same plots where we're looking at the real part of the visibility, Fourier transformed and time, what we were seeing was that these weren't as time stable as we thought they should have been. And our sort of physical model of it sort of was indicating that it should have been time stable. We should have been able to use this fringe rate technique, and it just wasn't working. So we had to dig a little bit deeper into understanding physically what is going on with this systematic. And so building on work that Nick did, I sort of dug in again to try to figure out what was going on. And so one thing that actually I think was the clue that led us to really understand what was going on is by looking at the Fourier transform of the visibility. So again, here is the foregrounds in the center, and we have a whole bunch of different visibilities with the same first antenna, different second antennas, and some arbitrary offset. And in the center, the foregrounds all look quite similar. These are different baselines, so they should look a little bit different. And interestingly, at the positive delays, the peaks all kind of line up. And at the negative delays, they don't. In fact, we're seeing these kind of slopes, which are a bit of a clue. And really what we were seeing was that the delay associated with this peak at negative delay had depended on the location in the array in a quite predictable way. So this is the location of that peak with this particular antenna, and we can do this for all pairs of antennas. And it looks like there's lower delays over here, higher delays over here. So that indicates that there's something being broadcast. So our model is that the voltage from this antenna, this is antenna 84, goes over a 150-meter cable to somewhere in the signal chain over here. I'll come back to that in a minute. And then it is broadcast out over the air into the other antennas. And then when we form a cross correlation between antenna 84 and say 141, we're effectively getting a bit of it that looks like an autocorrelation, which should be relatively non-fringing. It should be relatively stable in time and subtractable based on that. And that's the basic model that we are pursuing. So one could then take this and parameterize it. So there's a little bit of a detective problem here. So leaving the position of the emitter as that sole-free parameter, we find that the emitter is somewhere around here. And there's a fair bit of error here, and it's hard to quantify precisely how much error there is. But it does look like it's pretty consistent with stuff over here. And we can do the same, we can do the same exercise with the amplitude. And again, we're getting something over here is the best position for the emitter, though this is involves more parameters in the fit. And weirdly, the best fit power law is roughly 1 over d to the 2.3, which I don't understand. And if anyone has any ideas about why this voltage signal should fall off faster with distance than 1 over d, I'd be very curious to hear any E&M intuition on that. But regardless, that position is not coincidental. That is where a lot of our hardware, especially these receiver rators, which are literally receivers inside of special built mini fridges that were sitting out in the desert. This is likely where the signal was being re-emitted during HERA Phase 1. And so that's probably the source of this systematic. So as long as the array is not changing, this systematic should be stable. So instead of looking at each, binning all of our data together and then integrating down, instead we subtract the systematic on a sort of per epoch basis where the array is not particularly changing in time. And we find that actually allows us to subtract the systematic quite well, except down here at the galactic center where things are so bright that we've just given up on subtracting the systematic. And that has allowed us to now go deeper. So I'm not at liberty, unfortunately, to share how deep we're able to go. But we are seeing, again, power spectra now over more fields because we're able to, because we have a wider range of LSTs, and we're going, it looks like it's pretty consistent with noise, although it remains, statistical tests remain to quantify that within the EOR window. So this is really exciting. So right now, just on the rest of HERA Phase 1, we're pushing forward on an end-to-end validation pipeline, very similar to what we did with the limits that Nick talked about. And we're also running various statistical tests and jackknives. But just from a raw sensitivity perspective, we might see something like 3 times deeper in power spectrum units, just from raw sensitivity. I'm not sure that we're going to achieve that, but we should achieve something that is substantially better than what we put out before. And that's, again, without any real foreground subtraction or some of these more aggressive and potentially lossy techniques that we would like to bring to bear eventually. So meanwhile, we haven't, while that data is already taken, that system basically no longer exists. We've been replacing the entire signal chain, especially the receiver rators are gone, and we've been adding these Vivaldi feeds, which are allowing us to do this wide band from 50 to 250 megahertz. And that will give us, that gives us some new science capacity. But also, as we're building out, we're starting to get to the point where we have way more antennas than we can kind of deal with in a bespoke way that we've been doing thus far. So one of the efforts that we've been doing in terms of commissioning the full HERA array, Phase 2, as we're calling it, is by developing methods for automatic detection of bad antennas. So one of them, which is in a paper written by a graduate student at UW, Dara Storr, is based on this correlation matrix statistic that we've developed. So this is basically taking sets of interleaved visibilities, even in odd times, and cross-correlating them and renormalizing them and averaging that over time and frequency. And what one finds is that antennas that are not working, for example, if they're dead or they have clock distribution errors, they shouldn't correlate with other antennas. And so we get low correlation statistics, for example, for there's 37 and 38 here, all the way across the board. And so you can average across here, and you can see that these are dead. And other ones have a much more stable correlation statistic, which means that they seem to be working well. Likewise, you can actually use combinations of these, and I'm happy to go into details, or I can point you to the paper. You can use the combinations of these statistics to discover which antennas are cross-polarized. Literally, the X and Y polarization cables have been swapped somewhere in the signal chain. And so you can just then use that on a day-to-day basis to go out and tell the folks in the field, hey, can you swap these cables, and let's see if that fixes that, which is really great. We also, and I don't have much time to go into this either, we develop methods based on looking at the autocorrelations and extracting their statistical properties to look for things like outliers in shape and power and temporal structure that doesn't look right for whatever reason. So we can quantify that in terms of an outlierness or a z-score that automatically allows us to flag antennas quickly and be able to understand, which data is good, because when we're doing this very high sensitivity measurement, including a little bit of bad data in a very large quantity of good data can spoil the whole batch. So unfortunately, just the last season of observation, we didn't get as many good days of good data as we would have liked, and as many good antennas we'd like. We developed these statistical tests for finding bad antennas in part because we had so many, and unfortunately we had really limited site access. And it unfortunately looks like that's not going to get any better anytime soon in terms of travel to South Africa. So we're continuing to build out, and we've built much of the array in terms of the dishes, as Nick showed, but we haven't managed to actually commission as many antennas as we'd like. So we're pushing on that, but we do have enough data to do something interesting and to say something about especially the low band. So with this wide band, we're able to do simultaneously many more individual subbands where we could estimate power spectra. And Aaron Ewell-Weiss, who's leading this analysis, is looking at 9 different subbands across here, including some of these at the very interesting low bands, which eventually will allow us to say something about edges. So once again, one of the challenges has been cross-coupling. And instead of cross-coupling emitted from somewhere else in the array, we're now talking about cross-coupling between different elements. So Alec Josiadis, who's been leading some of this work, did a simulation of a subset of HERA antennas, looking at 2 identical baselines at different places in the array. And again, at this, without mutual coupling, the sort of fringe rate and delay structure looks the same because they're the same baseline. But when you add in this mutual coupling model, you start to get these sort of cross and slash effects that potentially add contamination to much higher delays, which would be a real problem. And I'm not going to go too deep into the numerical or the E&M intuition for why this is the case, other than to say we're seeing very similar things in our real data. We're seeing this sort of characteristic X pattern. And so we're going to need to apply a slightly more aggressive filter to deal with this. So instead of just throwing out fringe rate 0 as we have been before, instead what we're thinking about is only keeping the fringe rates that are consistent with the primary beam. And so here is where the foregrounds in the primary beam should be, and here is where the EOR in the primary beam should be, and everything else is either noise or systematics. So in principle, you could do this without incurring much loss, but in practice, this needs some validation and some end-to-end simulation to really build confidence in your techniques. But, and again, this is very preliminary, so I've obscured any axes here. It does seem like this technique of just keeping the primary beam is bringing down the systematics, and actually is a more optimal time averaging as well. So it's bringing down the whole power spectrum quite substantially, especially at low K and high Z. So here's we are forming power spectra at Redshift 17, but we are not ready to release any of them publicly.
So you have 2 minutes left, Josh.
Great, thank you. So in those last 2 minutes, I do want to just mention some of the science that we're looking forward to with HERA 350 in terms of what's next. And of course, this is optimistic and depends on actually achieving the results that we're looking for. But one of the things that I'm the most excited about is that with this full array, with a season of the full HERA 350 array, we should have way more than enough signal to noise to be able to detect a fiducial model of EOR like we see in blue. And especially if edges turns out to be right, we should be able to say something pretty definitive about the power spectrum at high redshift. And so that is particularly exciting. Another physics thing that I think is really important is that we'll actually be able to measure the reionization history of the universe. This is the kind of constraints we can expect to get with HERA compared to roughly what we know about the history of reionization, though this is a little bit old now. And with that kind of constraint, then we can go to our friends in the CMB community and say, all right, we can more or less eliminate tau, the optical depth to reionization, as a nuisance parameter for the CMB, which means that we can potentially enable, for example, better measurements of A sub S or equivalently sigma 8, and potentially enable a non-zero measurement of the sun and neutrino masses, which would be a really cool contribution to fundamental physics. So to sum up, in the first part of my talk, I talked about how we're pushing forward on a full season, now 94 nights of HERA Phase 1 data, that's 100 to 200 megahertz, using very similar techniques to what Nick talked about, and adapting our systematics mitigation techniques as necessary. Right now, we're busy cross-checking and validating those results, which could be as much as 3 times deeper, though I think we won't quite achieve that. We will definitely be substantially, I'm confident it will be substantially deeper than what we've published so far. And unfortunately, I'm not at liberty to say exactly how much more. Meanwhile, we've been commissioning our Phase 2 system, which allows us to have these wideband feeds and eventually follow-up edges. And while COVID has certainly limited our access to site, we spent a lot of time understanding how the systematics look in the new array so that we are ready to analyze the full season of data when we're able to fully commission the instrument. And finally, in the next few years, we should be able to do some really exciting astrophysics and cosmology with HERA if we can detect the 21 centimeter power spectrum and then tightly constrain the astrophysics of reionization with our measurements. So with that, thank you so much, and I'd be happy to take some questions.
Thank you, Josh. Great talk. If there are any questions, please raise your hand. I already see one. Lincoln, do you have a question?
Josh, thank you for the talk. I'm glad I've not muted myself again. The filtering in fringe rate is a little concerning. If I'm following correctly, it's doing that seems to weight what sections of the sky, or it changes the weighting of sections of the sky that you are permitting through your data analysis. So for instance, anything near the pole would be significantly down weighted, assuming you're using a smooth function to implement your filter. So at what point does that pose a problem for HERA? Is it
so you're talking about the less aggressive fringe rate filtering where we're saying let's throw out fringe rate 0?
Yes, or if you apply a smooth function to that, then you're throwing out 0 and a few pixels in this scat in your picture, a few pixels on either side maybe with various weights, but that means that the sky isn't really the sky anymore. Your data is now substantially a reweighted version of the sky.
Yes, you're absolutely right. It is a form of sometimes called beam sculpting, if you want to think about it that way. So the pole I'm not worried about because it is never in our primary beam. HERA sits at roughly latitude minus 30, which means we observe declination minus 30. So we have a roughly 10 degree full width half max beam. So we don't really see the pole. Fringe rate 0 is more of a problem for north-south baselines, where now the location of the primary beam here is dependent on the orientation and length of the baseline. So north-south oriented baselines actually have the primary beam also at fringe rate 0. And our strategy for those is actually just to throw them out. So that's a loss to sensitivity, which is unfortunate. And I'd be curious if there were ways of bringing it back. But we're basically saying we simulate an EOR and we say this is the kind of signal loss that we get if we throw out fringe rate 0, and we're willing to accept roughly 1% signal loss, which we then compensate for. But if you look at very short baselines with very short east-west distances, like pure north-south baselines, you actually would have very large signal loss there. So we just throw out the baseline entirely and don't bother trying to mitigate its systematic. So that's a loss in sensitivity, but that's something we're free to do.
Okay, thank you.
Okay, thanks, Josh. Unfortunately, we're out of time. So Ronnie, please ask your question on Slack. Then we go to our next speaker, who is Pixie Starr. And the title of her talk is Beyond Van Vleck, Correcting Digital Nonlinearities of Real-World Systems. We can see your screen, Pixie, and now we see your presentation, so go ahead.
Thank you so much. My name is Pixie Star, and I am a graduate student at the University of Washington. And I'm going to be talking today about correcting digital nonlinearities from quantization. Just to give you an overview of my talk, I'm going to talk about the Van Vleck correction, which addresses quantization errors and some of the built-in assumptions that come with that correction. I'm then going to talk about a real-world example using the MWA, which is a radio interferometer in Australia, and then talk about how I developed a correction for that example, because that example actually violates some of those built-in assumptions. So why this matters? So digital quantization errors are very small, so small that they're often considered to be pretty negligible in their impacts on data. But when we look at data from the MWA, we actually see that the nonlinearities from quantization mix with spectral structure that comes in from polyphase filter banks in the digital pathway and creates an effect that is time dependent. And additionally, this effect is also mixing with temperature dependent gains. So we actually see these residual spectral structures that are not only time dependent, but temperature dependent as well. And in this plot here, what we're seeing is that residual structure varying as a function of time. Now, these errors are very small. They're on the order of 10 to the minus 3. But in order for us to use this data for a power spectrum measurement of the EOR, we need to be able to get spectral calibration solutions that are accurate to 10 to the minus 5. So these small nonlinearity effects actually become really important when it comes to our ability to do that science. There are closed form corrections for digital quantization errors. Van Vleck and Middleton derived them, and written here are forms that are specifically tailored to the MWA. So these equations that I've just shown really depend on some key assumptions. So first, we're assuming that before quantization, the data streams are Gaussian distributed. Also, we're assuming that the effect of the quantization error is really to change the statistical properties of those data streams. Importantly, these equations also implicitly assume that there's a single quantization stage and that that stage is happening immediately before correlation. This is important because in real-world systems, we actually find that there are multiple quantization stages that are occurring throughout that digital signal pathway. So as an example, I want to look at the signal pathway for a single MWA antenna tile. The analog signal from the tile goes through filtering and conditioning, and then goes to the digital receiver where an analog to digital conversion samples the data stream into 8-bit numbers. Those numbers go to a polyphase filter bank, which performs channelization and takes the data streams from real to complex. From the digital receiver, the data goes to the correlator, where a fine polyphase filter bank performs a rechannelization of the data into finer channels before correlation. And I just want to note that for the MWA, we refer to these first and second polyphase filter bank stages as coarse channelization and fine channelization. So let's take a look at the digital portion of this pathway in a little bit more detail. That is the digital receiver and the correlator. When we start digging into the details of the implementations, we see that after that first polyphase filter bank, there's a requantization that takes the data to 5 plus 5-bit real and imaginary pairs before it goes from the receiver to the correlator. And within the correlator, after that second polyphase filter bank channelization, the data is requantized to 4 plus 4-bit real and imaginary pairs before it goes to correlation. But that's not all. We can dig even a little bit deeper into the fine polyphase filter bank. And there we find that between the front end stage where filters are applied and the FFT, there's a requantization stage that takes the numbers to 8 plus 8-bit pairs. And this particular requantization stage is actually implemented asymmetrically. So the implementation for negative and positive numbers are actually different. I want to point out that having all of these requantization stages in the digital signal pathway is not something that is unique to the MWA. So for example, in the HERA correlator, every butterfly stage of the FFT is accompanied by a requantization stage. So what can we do with this? So this 4-bit requantization stage does occur immediately before correlation. So we can use the closed forms that I showed earlier. And I've done that and implemented those corrections into PyUV data as part of a reader that ingests raw MWA correlator files. I thought that was the hard bit, but it turns out that's actually the easiest part, because now we have this 8-bit asymmetric requantization stage. It is not before correlation, it's before the fine polyphase filter bank FFT, so it actually occurs on coarse channelized data rather than fine channelized data. So using the closed form solutions doesn't really work. Since we can't use those, I moved to simulation. So I don't have a simulation of the entire digital signal chain yet, but I have simulated this particular piece. So I've taken data streams sampled, I've simulated data streams sampled from Gaussian distributions and taken them through a simulation of this asymmetric requantization and the FFT. And with those, I can look at the effect of that asymmetric requantization on the statistical properties of the signals. In particular, I look at the impact on standard deviations, which correspond to our autocorrelations, and the impact on covariances, which correspond to the cross correlations. I've done this simulation for both the autocorrelations and the cross correlations, but I'm just going to talk about what I did for the autocorrelations here, but I'm happy to discuss the cross correlation process in questions or later. It's very similar to what I did for the autos. So doing the simulations, we get to see what the effects of this 8-bit asymmetric requantization are on the statistics. So this requantization changes the standard deviation of the coarse channel data, which means that then after the FFT, those fine channel standard deviations have also shifted. Also, because this requantization is asymmetric, we get a non-zero mean in that coarse channel data, which puts power into the DC bin coming out of the FFT. And we see this in our data. We see a spike of excess power in one of our fine channel bins in our actual data. So with the simulation, we can see the impacts on the standard deviations. So here on the left is a histogram of simulated analog correlator standard deviations, or what I would expect to see if there had not been a requantization stage. In the center are digital correlator standard deviations with those 8-bit quantization errors. And on the right are those same digital correlator standard deviations where I have applied the correction that I found through these simulations. So we can really see here that the effect of this 8-bit requantization is to shift the standard deviations. And the amount that those standard deviations shift is really dependent on the standard deviation of the corresponding coarse channel. This makes sense because the 8-bit requantization stage is actually happening in that coarse channel stage. So the simulations for the autocorrelations exist in kind of this 2D space that is the fine channel standard deviation and the coarse channel standard deviation. And those are the observables that we can get from our actual data. So the simulation, the data has been simulated kind of over this entire space, but I wanted to see where our actual data kind of lives within that 2D realm. And on the left, we can see this region. This is a histogram of the actual MWA correlator data. And we see that it lives in this kind of streak in this space. And our the fine channel response is pretty smooth. And so we see that here where our fine channel standard deviations and our coarse channel standard deviations, we don't expect them actually to be wildly different. They're going to be kind of similar to each other. Now in the center plot, I have the mean difference of the analog correlator standard deviation and the digital correlator standard deviation with quantization errors. So this is kind of showing in that region what that shift looks like of those standard deviations. Now here, the center plot is the same. I've just taken the color bar and pinned it to the color bar of the plot on the right, kind of for consistency. So on the right, what we see is the analog correlator standard deviation minus the digital correlator standard deviation with that, with the correction that I found applied to it. So we see some really nice agreement there. And that's very exciting. So I have a little bit of time, so I'm going to talk a little bit about my bonus plot, which goes into a little bit of the cross correlation correction. There's a lot going on here, so I'll go through it, but if anyone has any questions, please feel free to ask. The cross correlation simulation is very similar to the auto correlation, looking at covariances now instead of standard deviations. And we have a bigger parameter space because now we have the coarse channel standard deviation for 2 different antennas. So here is just a slice into that space where the coarse channel standard deviations of the 2 antennas are fixed. And I'm looking in that slice at the covariance of the analog versus the digital. This plot has a lot going on because it encompasses also that 4-bit quantization stage that I brought up earlier. But if we want to just zoom in on the effects of the 8-bit, this third plot on the top row shows that the slant that we get from that 8-bit requantization stage. And this spike here is not related to this particular value of 0.15, but it's just that DC power that shows up in our center fine channel.
You have 2 minutes left, Pixie.
Thank you so much, André. And then a corresponding plot is the second from the left on the bottom, and that shows the same simulated data with the correction applied. So I should state actually that these are difference plots. So they're showing the difference between the analog correlator covariance and the digital correlator covariance, the top having those 8-bit quantization errors and the bottom having the 8-bit correction applied, including the subtraction that removes that excess DC power. So this is all very exciting. And I'm working on applying these corrections through PyEV data onto our actual data and taking that all the way through the power spectrum pipeline. So I would say that a couple of kind of big level takeaways that I've gotten from doing this work are that these requantization stages are actually very important, and a design principle should be to limit them as much as possible. And the ones that are included in the design should be carefully tested to make sure that their implementations are error-free and to understand what the effects of those implementations will be on the data. And we're seeing this in practice with the MWA, with the new MWA correlator, which is currently taking data, and the digital receivers, which are in development, that a lot of really careful testing is being done to understand and potentially remove effects of those digital system implementations. So this is very exciting for the future of that array and our science with it. For existing systems that already have these requantization stages in them, it is possible to go in and to model them and do simulations and understand the effects of these actual real world implementations. I will say though that while it is possible, it does require really building a deep understanding of the actual implementation of those digital pathways. So with that, I want to give a thank you to everyone at the MWA who offered me their apocryphal engineering knowledge of the actual implementation of the MWA digital signal pathway and answered my many, many emails as I was digging deeper and deeper into this system.
Thank you, Pixie.
And with that, thank you.
Thanks, Pixie. Very interesting.
Thank you.
Are there any questions? If so, please raise your hands using the reactions. I see that Lincoln already has his hand up. Lincoln, go ahead. Lincoln, I don't hear you. You are unmuted. Let's try someone else then. Any other questions? I can ask one question. Well, you're saying that design principle limit the number of requantizations, but wouldn't you say that basically you sort of solve the problem because you correct for it? So isn't it the case that we don't have to design for it anymore?
Well, I suppose it's a bit of a trade-off of how much manpower we want to kind of spend after the fact going in and removing effects versus not having them. Initially, building these simulations and developing the corrections and all of the testing is possible, but I wouldn't say that it's trivial. Quantizations that can use the Van Vleck correction are easier to correct. So I think that ideally would be to minimize the amount of that work that has to be done.
Okay, clear. Thanks. Is there any last short question? Yeah, Jeffrey, go ahead.
If you were starting from scratch and had an infinite budget, what would you do? Or what would be the first thing you would do to make this problem disappear?
So that's a good question. So I think, like I said, limiting, so I'm assuming I'm designing a new instrument. So limiting requantization stages, and then in the places where, some quantization is always necessary, keeping those, as many bits as is reasonable. So, the higher sort of bit number we have, the smaller these effects become.
What about floating
And then
point? Could you just do these calculations floating point?
that is a good question. I think that with FFTs, I think that some care still has to be taken using floating point numbers. I haven't looked as deeply into that though, so I can't say exactly what the effects of those are, but I think that I would have to look a little more closely at, like, say, what a floating point FFT kind of might generate in those stages versus, you know, one that's doing these different requantization.
Thank you.
With that, I would like to end the questions. Thanks a lot, Pixie. Very interesting. And then I'll welcome to the floor our next speaker, Julian Munoz, who will talk about cosmology from 21 centimeter radio. Go ahead, Julian. Take it away.
Thank you, André. Thank you to the organizers and everyone for this great conference. So I'm going to shift gears entirely from the previous three talks, and I want to talk about theory, in particular about what 21 centimeter can do for cosmology. Focusing on what we can do in 2021, but in general, what in the future might have in stock for cosmology. So Nick showed a picture like this one in his talk in the review, where you can see sort of like the groundwork of cosmology that goes from the epoch of the CMB, cosmic dawn reionization, to the local universe. And in 2021, cosmology is an interesting position. Because of all this, we actually only get to measure the beginning and the end so far. And from these two sides, cosmology has learned a lot. And in case that, you know, to bring everyone up to speed, in case you haven't been keeping track of all the things, we know there's dark matter. We know dark matter appears to be cold and collisionless, which for us cosmologists means that it clusters at all scales. It doesn't interact with anything. It's just very boring and inert. And I want to show you a cartoon of how we know this. And it's by studying the clustering of dark matter at very different scales. So these are different measurements of where dark matter is clustering. In the x-axis is the cosmic time, in the y-axis is the scales that different experiments probe. So here you have it in terms of the halo masses, and here you have it in the terms of their wave numbers, if you're thinking of the matter power spectrum. And you measure the very early universe of the CMB at Redshift 1000, you measure some large scale fluctuations. And then in the local universe, you have all sorts of probes from lensing, Lyman alpha forests, galaxies, and even the Milky Way itself at Redshift 0. As they probe different ranges of scales at different ranges of quantities. And in all of these that we probe, dark matter seems to be cold, which again means boring, inert, nothing interesting. But we don't know what's happening at early times and at small scales here. This is when the first galaxies formed in the universe. And this is where 21 centimeter data can really shed light on both galaxy formation and the actual nature of dark matter itself. Because if dark matter wasn't cold, this is where you would expect to see deviations from this behavior at small scales and at early times. Another interesting problem in cosmology nowadays is that there's tensions between these two sides of the universe. And you might have heard of the H0 tension, which is the parameter that tells us how quickly the universe is expanding. We get measurements from the local universe at Redshift 0 and measurements from Redshift 1000 inferred to today. And they disagree wildly with each other. The supernovae at Redshift 0 tells the universe expanding much faster than the CMB tells us. And this is in this cartoon by Adam Rees, where you get the early route, what he calls out the standard rulers, things like the CMB, with very acoustic oscillations, give you a value of 64 kilometers per second megaparsec for each knot. Whereas the late route, things like standard candles, gives you 73, much, much higher. And 21 centimeter will be in between these types of observables. So it can actually tell us what's happening in between these two eras. So with that sort of motivation out of the way, I'll tell you specific things that, as Nick mentioned, 21 centimeter will help us a lot. I'll tell you specific things it can do for us. I'm going to start telling you about the theoretical predictions. This is one of the simulated 21 centimeter signals. Before I tell you details of where it comes or what it has, let me give you the broad overview. Going from left to right, cosmic time evolves. The white on the left at very low frequencies, very early times, means there's no signal until at about Redshift 25 or so, we start seeing some absorption. And that's when the first galaxies form in the universe. And you start seeing these islands of blue that gets deeper and deeper and deeper. And eventually, at some point, this turns around. You start seeing heating, which are these islands of red, due to X-rays, which, as Nick talked about, we can actually say something due to HERA nowadays about these X-rays. Otherwise, we have no idea what's happening. And then slowly you get more and more heating until the universe is fully heated, fully red. And you start seeing islands of white, you start seeing reionization. And this reionization eventually takes over, and by Redshift 5, the whole universe is reionized. And these are very recent simulations that we run in this paper. They run with 21 cm fast, which is a public simulation code that we augmented to have pop-3 stars and all relevant feedback on these pop-3 stars. So for the first time, we have pop2, pop-3 stars, the whole stellar population as far as we can tell. And we run like a whole set of public simulations you can download. So it has all the bells and whistles. And one of the interesting things that it has for the first time late reionization, where you can see these islands of neutral hydrogen at redshift 5 point something, which seems to be what the Lyman alpha forest wants. So that's something good. Also predicts the luminosity functions. There's a lot of interesting astrophysics. But again, we came here to talk about cosmology. And as most of you are aware, there's two ways to measure this 21 centimeter signal. There's the global way, which things like edges, for example, do, which I'll talk about in a minute. And the fluctuations, like in the case of the CMB, would be like Planck. And I'm going to talk about HERA for a minute. So these are the two ways. This is the theoretical signal. Another thing, this is what the global signal will look like. It has the, it goes down, the cosmic dawn trough, it goes up, and it slowly gets reionized towards zero. And this is the first way you can learn cosmology, is using 21 centimeters of thermometer at high redshifts. And what I mean with that is that the 21 centimeter intensity is given by some constant, which roughly is about 30 millikelvin at cosmic dawn, times 1 minus temperature CMB, which we know really well, divided by the spin temperature of hydrogen. So if you have measurements here of the 21 centimeter signal, you have measurements of the spin temperature of hydrogen, which tells you whether hydrogen is cold, hot, and what is happening to it. It's telling you about the Igm in the early universe. And you can use this to tell what is heating the gas, if anything is heating the gas. And Nick told us about the X-rays from the early universe. But what I'm going to tell you about, is that you can learn about cosmology. In particular, dark matter can cool down or heat up the gas. And this gives you different predictions in this era. And you can actually use the data to look for dark matter. And the 2018 status of the field was that edges had their first detection, which once they subtracted the foregrounds, looked something like this. And I'm not going to talk about whether it's systematics or any of that. Just take this as a sort of the reach of what 21 centimeter experiments can do for us, rather than whether this is a cosmic signal. It is the 21 centimeter temperature versus frequency. And this trough is centered about redshift 17, which is roughly where theory predicts, but the depth is huge. It's about minus 0.6 Kelvin. So you were to put the minus 0.6 Kelvin here on the left-hand side, you get a very, very small spin temperature. It has to be much, much colder than the CMB. So to put it pictorially, the spin temperature has to be below here. So this is a plot similar to the one Nick showed and we put in the HERA paper, where you can have the standard CDM prediction. I'm assuming here full Woodhausen field coupling, which at late times will be for sure true, at earlier times will not. And there's a CDM prediction, and edges require you to be below this line, which is tricky. But in this paper with Avilo, we argue that one of the few ways to make this thing work is to have a fraction of dark matter be emitted charge, which means as an electric charge. So it can actually interact electromagnetically with the protons and the electrons and cool them down, because dark matter is cold and boring. And this gives you this blue line over here, which agrees with edges. But as you see, this line will keep being cold at later times. And by using low redshift data, we can actually test this model. So now is where 2021 comes in. Nick already showed this plot of where the HERA limits currently stand, and particular Redshift 8 limit he talked about tells us about X-ray heating. I'm going to talk about the Redshift 10 data point, which is the earliest of these deep points that we have. So if you were to translate these limits, again, using using this translation to lower T-gas. Our fiducial models are well below these limits. But if you lower the gas temperature in these fiducial models, all the curves will go up. So at some point, they will cross these lines. The HERA data can be interpreted to have these limits on the gas temperature. The Redshift 8, again, is telling us there has to be some X-ray heating. But the Redshift 10 is telling us that this milli-charged dark matter model is not in agreement with the HERA data on Redshift 10. So what you should interpret from this is that either something has to happen between Redshift 17 and Redshift 10, like X-ray heating of the dark matter, of the gas, which we expect to happen anyway, or dark matter is not behind edges. And of course, what we would like to do is eventually extend this whole analysis of HERA data to the redshifts that edges is covering. And Josh talked about it in his talk. So this is, stay tuned to see what we can say. But for now, we have a limited statement we can make. The second thing you can do for dark matter is study whether it's cold. So forget about the collisions. Let's think about the cold part. And again, cold means clustering at all scales, small and big. And this is what cold dark matter does, for example. Whenever you have a Milky Way like satellite, a galaxy, so something in the center here, there's a big halo that is dark matter that hosts it. And there's a lot of small dark matter halos that live around this. These are satellites. And some of these satellites will host galaxies like the Magellanic Cloud. But when we look around us, we don't see something like this. We see something more like this. We don't see a lot of tiny satellites. We see some of the big ones, but we miss a lot of the small ones. And that could just be because of astrophysics. Galaxies fall into the Milky Way halo, they get disrupted, feedback is complicated. But people argue that it could be because dark matter is not cold, but instead warm, like here in the simulation, where warm means that it has thermal motions. So it has a velocity that disrupts all this small scale structure. And if this is the case, this is not just an academic question, it's telling us where dark matter comes from. Warm dark matter should be a relic of the early universe. So if this was the case, we would know exactly what dark matter is. But again, as I said, at redshift 0 in the Milky Way, this is very complicated, very nonlinear. And 21 centimeter can help us here by looking at when the first stars formed. The first stars form in tiny galaxies, smaller than the counterparts today, smaller even than most of the Milky Way satellites. And they didn't fall into a bigger galaxy. You're seeing them form for the first time. So you can actually learn what dark matter is doing at those times. So this is a cartoon of what is the typical halo that is forming in the universe as a function of time or redshift. So this red line tells you that the growth of structure grows exponentially. So you start with very tiny halos, and over time they grow bigger and bigger and bigger and bigger. But it isn't until these halos are of order 10 to the 5 solar masses or so that the gas inside can actually cool through molecular line transitions. And when this happens is when the first stars will form. Gas will cool, they collapse into a star, and you get light for the first time. And that's when 21 centimeter will turn on. That's when you get Woodhouse field effect. If your dark matter was not cold, if it was warm, for example, there'll be no halos below some cutoff because of these thermal motions. And for a 5 keV mass, which is how we parameterize this dark matter, that is the best limit from the Lyman alpha forest, there's no stars until about redshift 17 or so. So there is an order unity change of how cosmic dawn proceeds. So everything will happen much later, and this is something we can go and test in data. And in particular, in this series of papers, I collaborated with different people in cosmology and particle physics to implement their models of warm dark matter with and without self interactions to see how the 21 centimeter signal changed. So here in the top panel, I'm showing the global signal, and in the bottom panel, the power spectrum at a particular wave number. And the color of these lines represents the mass of the dark matter parameterized by the wave number at which there's a cut in the power spectrum. So the black is CDM, this is standard CDM prediction. And then warmer colors means warmer dark matter. And all the lines with the same color have different amounts of self-interactions. So these green lines all have a 5 keV, again, the best limit we currently have from the Lyman alpha forest. And they are all significantly different from CDM. So this is telling us that just by looking at when the signal first goes down and when the peak is, we can actually determine what dark matter is made of. And this is something that is entirely within the reach of HERA, edges, and all the other 21 centimeter experiments.
You have 2 minutes left, Julian.
Awesome, thank you. So the takeaway home from this message, take a home message from this is that 21 centimeter experiments will probe this green region over here in this plot that I showed. So early times, very small scales when the first galaxies formed. So if dark matter was warm, it was fuzzy like an axion, self-interacting, these regimes where you would expect changes, and you're seeing them to the left of the nonlinear line. You're seeing them before all the nonlinear effects kick in, which is interesting for cosmology. So the last thing I'll say in the last 90 seconds is that you can measure the expansion rate of the universe at earlier times than any other way. So these are different measurements from, let's say, standard candles and standard rulers, which disagree with each other. So here's the expansion rate in the y-axis versus redshift, and there's a gap between these. But we don't know what's happening in between us and the CMB. Once you go above redshift 2 or 3, we have no idea. And the way we make progress in complicated fields like galaxies is using standard rulers like the BAO. We know the galaxies tend to be correlated by some sun horizon. But we also know that in addition to densities, there's velocities. And these velocities are more and more important in the early universe because they redshift away by today. So whenever there's density, there's also velocities, and they give you a new type of standard ruler. So our velocity-induced acoustic oscillations, or VAOs. I don't have a lot of time to describe the details of the physics, but if you're interested, please reach out. But this is something that HERA will be able to measure. And we hope to get a few percent level measurement of the Hubble expansion rate at redshift 15 to 20, so during cosmic dawn. And if so, this will actually allow us to complete the picture of what the expansion rate is doing between us and the CMB. To summarize, the 21 centimeter line will allow us to map the intermediate cosmos with radio telescopes. So intermediate between us and the CMB, where there's a big gap in our knowledge. And of course, this will allow us to measure the first galaxies forming, which is extremely interesting, but also will do a lot for cosmology. And in particular, I've told you how to test if dark matter interacts with us, if it's fuzzy or self-interacting, anything without our sector, any other way that you cannot probe in the lab. And finally, to tell us what the expansion rate of the universe is at redshift 10 to 20. Thanks.
Great. Thank you, Julian. Very nice talk. If there are any questions, please raise your hand. And if not, I'll take the honor of the first questions. There is a question. Miguel Morales, go ahead.
Hi, thank you. Very fun. I just need to go read a bunch of your papers, but on the last thing about the velocity effects, do you need to get to BAO scales in the HERA measurement in order to get those, or can those, what's behind the question is the interaction with the wedge and various things like that, and how low in K you actually have to go and how approachable this is. So if you could
the lower K you get, that's a very good question. The lower K you get to the better. In principle, when I did all the forecasts for these few percent, I took the standard wedge with a 0.1 super horizon buffer, 0.1 inverse megaparsec, that is. If you were to cut anything below 0.5, you will not be able to do this. So you do need the BAO scales, but you don't need to go as low as, like, say, galaxy surveys do. Getting to 0.1 or 0.2 is sufficient.
Great, thank you.
Thanks. And that is, by the way, that is because it's an order unity wiggle. Like, it's not a tiny percent level wiggle like the BAO. This is like 100% oscillation on top.
Great. Are there any other questions? We still have time. What do you think, Julian, of doing a global experiment at even lower frequencies? Would that help?
That would be fantastic. If you were able to reach the dark ages, so like you were able to push this to even earlier times where there's no heating, nothing astrophysics, that would be great. My fear with that is for the global signal, that seems doable. For the fluctuations, it seems extremely difficult because the fluctuations are smaller, and synchrotron, atmosphere, all these things get worse and worse and worse. But in some people argue that could be the final frontier of cosmology, measuring primordial non-Gaussianities at redshift 50, say, which no other cosmological observable, large-scale structure, CMB, none of them can do it.
Okay, great. That's very interesting. Thanks, Julian. Thanks again. Then we'll go to our next speaker. Next speaker is Anniek Gloudemans, and she will talk about using low-frequency observations to study and find redshift larger than 5 quasars into the Epoch of Reionization. Go ahead.
Yes. Can you see this and hear me?
Yes, all looks good. I see your slides.
Okay, great. So hi, everyone. I hope everyone is still awake across the different time zones. So my name is Anniek Gloudemans. I'm a PhD candidate at the Light Observatory. And today I'll be talking to you about using low frequency observations to study and find high redshift quasars into the Epoch of Reionization. So this work I've been doing mostly for the past year, and I just want to say a big thank you to the organizers, of course, of this conference, and all of my collaborators and my supervisors, Ken Duncan and Huub Rutgering. So I just want to start with a little bit of a brief introduction. So you've already seen many pictures that look similar to this today, but I'm going to go a little bit more into the high redshift quasars. So one of the main reasons why we're actually interested in high redshift quasars is because they're really excellent probes of the Epoch of Reionization. So this epoch is really the last big phase transition of our universe when it went from neutral to ionized. And we can use these quasars to probe the neutral IgM at that point. So in the last decades, people have spent a lot of time trying to look for high redshift quasars, and they have found about hundreds of these objects. And of course, also the properties of these objects themselves are very interesting on its own. So there also have been some efforts in the radio, and mainly in a little bit higher frequency radio observations. So for instance, this study of Bañales et al. Is looking at high redshift quasars at a frequency of 1.4 gigahertz using the first survey. So here you can see one of the plots where they are looking at the radio loudness of these quasars. And what they find is very similar to other previous studies, is that about 10% of these high redshift quasars seem to be radio loud. So the majority, about 90%, seems to be radio quiet. But actually also recent studies have found that there does not appear to be really a physical difference between these radio loud and radio quiet quasars. So this is really more a matter of definition. But one very important reason is why we are very interested in these very radio loud quasars is because potentially we could use those as new probes of the neutral hydrogen using the 21 centimeter absorption line. So in the other talks today, usually we were thinking of measuring the 21 centimeter signal by itself, but we could also use quasar sidelines to measure the 21 centimeter absorption. But we do need the right targets that are bright enough and into the EOR to do this type of measurement. And also from an evolutionary standpoint, these objects are very interesting because they're usually associated with some of the most supermassive black holes in the universe. And also they're often associated or often found in protocluster environments. So this is a famous example of the spiderweb galaxy at a little bit of a lower redshift. So most previous studies have been in the gigahertz radio regime, but now with LOFAR, the low frequency array, we can really push these statistical studies to lower frequencies. So that's what we have been doing. So I guess most of you are already familiar with LOFAR, but here's a quick picture of its main array. So that's based in the Netherlands with stations all across Europe. And well, the frequency range is about 30 to 200 megahertz. But I'll mainly be talking about the LOFAR 2 meter sky survey. So currently, data release 2 is almost coming out. And here you can see in the black contours, this data release 2. So you can see compared to data release 1 here in the yellow, it's really, really a big upscaling. So here on the right, you can see some of the stats for the LOFAR 2 meter sky survey DR2. So it's about 6,000 square degrees of sky at 144 megahertz and a 6 arcsecond resolution. And it reaches a noise level of about 0.1 millijansky. So this is pretty deep for a low frequency all sky survey. So this is a great data set to be studying the low frequency properties of high redshift quasars. So for this study, we used a sample of Rosencross 2020. So this consisted of 488 known quasars above a redshift of 5. And it also came with some ancillary near-infrared catalogs, so that was very handy. And here on the left, you can see the LOTS DR2 footprint together with these quasars and about a fourth of these quasars, so 115, are located in the LOTS DR2 area. So that's the sample we have been working with. And here you can quickly see the redshift distribution of the sample. So you can see most quasars are located around 5 and a redshift of 6. And this work is already available in arXiv if you're interested. So what did we find? Out of the 115 quasars, we detected 41 of these quasars tentatively at a higher than 2 sigma level, with about 19 at 5 sigma or higher. And here on the right, you can see the radioluminosities for these quasars. And you can also clearly see that this population is really getting more numerous whenever we go to this lower radioluminosities. And actually, we were very, very happily surprised with this high number of detections, so around 35% of the quasars we detect in LOFAR. So of course, we're also very interested in the whole population. So that's why in the 4 different redshift bins, we stack the different quasars. So here you can see in the black points, the radioluminosities of these stacks. And here on the left, you can see the cutout images of the stacks. And we have a strong detection in the first 3 redshift bins. So as you can see, we have to go deeper with lots to be able to reach this limit, but actually we are already reaching this limit in the LOFAR deep fields. So then, of course, it's very interesting to take a look at the radiospectral indices. So for this, we also used the first survey at 1.4 gigahertz. And as you can see in this survey, there's 9 sources detected. And you can also see that there's quite a lot of spread in the spectral indices of these sources. But in general, these quasars seem to be pretty flat in their radio spectrum. And of course, to again get a feeling of the average population, we do a stacking analysis using some bootstrapping of all the quasars in a LOTS DR2 and at first, and then we find a median spectral index of -0.3, which is actually very similar to what Gurken et al. Found for a lower redshift sample. So quite flat. And to compare this also to some of the higher radio frequency work, we scale it to 5 gigahertz using these spectral indices. And we again also try to get this radio loudness fraction. And so if we do the same, we scale our 150 megahertz to 5 gigahertz, and we use all the optical and near-infrared data we have, do some SED fitting, and then find the 4,400 angstrom rest frame flux. We actually also find a radio loudness fraction of about 10%. So this is very similar to what other work has found previously. And then if we put this in a little bit of a bigger picture, so here we can see all the quasars we detected in a LOTS DR2, and we compare it to some lower redshift quasars at the SDSS, but also some high redshift radio galaxies. And you can already immediately see that there's kind of a gap here in this area. And we think this is partly a selection bias effect, because these quasars here at high redshift, all but one of them have been selected using purely optical near-infrared surveys. And all of these radio galaxies, in fact, have been selected using radio surveys. So it's not really surprising that these radio galaxies have way higher radioluminosities here than these quasars. So now with this new LOFAR data, we want to try and see if we can find more objects in this space. So that's why we started a campaign trying to find new quasars above redshift of 5. So for this, we have been using the DESI Legacy Imaging Survey. So this is an all-sky optical survey, and it's quite a lot deeper than band stars and SDSS. So it's really giving us a new space to explore. And we've been combining this with the LOTS DR2 survey. And one of the main advantages we hoped this would give us is that the fact that we have a radio detection actually decreases the number of stellar contaminants that you usually have in optical surveys. So here on the right, you can see one of the examples for candidate selection. So the Legacy Imaging Survey gives us GR and Z-band images, And then we start looking for the Lyman break between the R and the Z band. And we look for our LOFAR detections. So unfortunately for this survey, the I band is missing for the all sky. So that means if we look between the R and the Z band, actually our redshift range is pretty large, between 4.8 and 6.4 roughly. But luckily, we also have some machine learning based photometric redshifts by Duncan 2021. So this paper has just been submitted by him. And here on the right, you can see one of the figures and how this photometric redshift performs compared to known spectroscopic redshifts. And this machine learning based code is actually performing a lot better than some of the previously used photometric redshift codes because it's taking a different parameter space for this rare population. So for our candidate selection, we used only sources above a photometric redshift of 3.5. And then finally, in our selection, we also use some templates fitting in the SD fitting code easy, using some AGN templates from Brown et al. So here on the right, again, you can see an example of such a candidate. And in the end, also by some visual inspection, of course, we find about 130 high redshift candidates. So then, of course, the next step is some spectroscopic confirmation. So for this, we've been using two different telescopes. So first of all, the Hopi-Eberly telescope in Texas, here on the left, and the Subaru telescope in Hawaii on the right. And well, as of last week, we have 42 candidates observed in total. So here I show you the results. So we found in total 14 new quasars above a redshift of 4.9. So here you can see the different spectra for the 14 quasars. So they range all the way from 4.9 to 6.1. So here there's two quasars at 6.1 at different radio fluxes. So our success rate is really high, 33%. And yeah, this is actually a lot higher than can be expected just from optical detections alone. So that's really great. But now, of course, the question is, are we actually probing this new parameter space? And when you look at this figure, I guess the answer is not really, because you can see that still our new discovered quasars are very much in this regime down here, except for maybe this one and these two. But actually, some of the candidates we had over here all turned out to be contaminants. But then if we do look again at this radioluminescence plot, we do see that we are actually probing a slightly different space. So we are going to lower optical luminosities and higher radioluminosities here. So that is a good sign. But then if we look purely at the optical, you can still see that compared to known quasars, so here in the blue and here are new discovered quasars, these are actually still very similar in the optical. And the same is the case for the near infrared and the infrared. So here we were hoping to find some quasars outside of this this parameter space, but actually all the ones outside seem to be contaminants. So that is unfortunate, but you know, more data to come. So more spectroscopic observations are still on the way, both of Subaru and the Hopi-Eberly telescope. So we hope to get some more confirmations. And we also are planning to try to do some follow-up observations, for example, with the VLA to take a look at the radio spectrum of these sources and some near-infrared spectroscopy to get to know more about supermassive black holes. And currently, we're also trying to push to lower declinations with LOFAR and use even deeper optical surveys. So for example, the hypersur prime cam survey is even deeper in optical. And of course, I cannot really give a talk without promoting WEAVE LOFAR. So WEAVE is a multi-fiber spectrograph on the William Herschel telescope. And here you can see part of the positioner. So it's about 1,000 different fibers. None of these fibers can take simultaneous spectra. And this is already placed on the William Herschel telescope on La Palma here. And soon after Christmas, it will hopefully finally start observing. And for VIII, for the white survey, the plan is to take spectra of all sources above 8 millijansky. And this will really uncover, hopefully, some new high redshift sources.
You have 2 minutes left, Anniek.
Yeah, almost done. So we will be detecting the Lyman line. And then, of course, well, JWST has some nice programs approved. Going to be looking more into specifics of these high redshift sources. And with the Euclid, we can expect to find a lot more interesting faint sources also with radio emission. So then quickly my conclusions. We do detect a high fraction of known quasars in LOTS DR2. And we conclude that these radio detections are a really useful tool for selecting high redshift quasars. So we are basically changing the selection biases from optical surveys. But we do need to find more radio bright sources to really be able to do this 21 centimeter spectroscopy, which is in the end the ultimate goal. But we expect to potentially find hundreds of new redshift higher than 5 luminous radio sources with VIII. So my expectations are very high. So thank you, and I'll take any questions.
Great, thanks a lot, Anniek. If there are any questions, please raise your hand. In the meantime, so how sure are we that those bright quasars exist? Because
well,
it was, yeah, go ahead.
We know of at least one. So for example, there is this one source of Peladita at redshift of 6.1, which is a 50 millijansky source. So that one is pretty bright, but yes, they are very rare. And of course, like the highest redshift radio galaxy at this moment is still at a redshift of 5.7. Yeah, so I do think these sources exist, but I also do think that we need to look very carefully for them.
Okay, thank you. Sarah, Leslie?
Great talk, Anniek. I was wondering, what are the main sources of contaminants for your sample?
Thanks. That's a great question. So actually the main contaminants we have is something we did not expect, which is they seem to look like brown dwarfs. And if you're familiar with the field, you know that usually we do not detect brown dwarfs at 150 megahertz. So what now seems to potentially be the case is that we're actually having some wrong associations. So we're not completely sure if the radio detections that we have are actually coming from this brown dwarf, because brown dwarfs are usually the main contaminant in optical surveys. So we're still figuring out whether these radio detections are actually coming from those brown dwarfs or not. Maybe part of them do, part of them don't, but this still needs some more investigation.
Really interesting, thanks.
Okay, Joe, did you want to still ask a question? I see you lowered your hand.
Sure, yeah, sorry, it was on the same. Profiles yet, or are you thinking about that, or where is that sitting in terms of your follow-up studies?
So these new quasars that I found are not bright enough to do the 21 centimeter absorption. So at least not with LOFAR. So I think this is really the type of source that will be useful for SKA in the future. But for LOFAR right now, we need a very long integration time. So yeah, that's also why one of my main conclusions is that we still need more radio bright sources for this. So I also really hope that VIII LOFAR is going to give us some of these. Yeah.
Cool, thanks.
Great, thanks again, Anniek, very nice. Then our next speaker is not going to present live, but I will start a video.
Hello, everybody. First of all, let me thank the organizers for giving me the opportunity to present this work at this conference. And today I would like to talk to you about one of the latest discoveries that we had with LOFAR in the field of galaxy clusters, and that we named radio megahalos. So this is the outline of the talk. I will start with a very brief introduction on radio diffuse sources in galaxy clusters, and then I will give you a little bit of the novelty that LOFAR brought into this field. And then in the last part of the talk, I will finally talk about this newly discovered phenomenon in galaxy clusters that we named radio megahalos. Let's start with radio diffuse sources in galaxy clusters. So some galaxy clusters host diffuse synchrotron sources on a typical scale of 1 megaparsec. These are only some of the images or the most beautiful images that we have, but actually these sources are quite common in galaxy clusters. We used to divide, to classify these sources in radio halos and radio relics. Radio halos are sources located at the center of galaxy clusters, and their emission roughly follows the X-ray emission from the thermal plasma, from the intracluster medium. Radio relics instead are more elongated, and they are found at the periphery of galaxy clusters. We believe that the formation of these sources is connected to the formation of galaxy clusters themselves. Galaxy clusters in the hierarchical scenario form via subsequent mergers of smaller groups or smaller substructures. So in a very simplified view, you can imagine two galaxy clusters, they collide, they merge into a bigger cluster, and this event, the merging event, is extremely powerful. We are speaking about 10 to the 63 ergs on a timescale of about 1 giga-year. And during this extremely powerful event, shockwaves and turbulence develop in the intracluster medium. And both shockwaves and turbulence are able to accelerate particles basically via Fermi types of mechanisms. And this particle then travel through the cluster magnetic field and emit synchrotron radiation. Here we have a simulation. The green is basically the thermal plasma, the ICM. This cluster is falling into a larger cluster. This is the merging event. And you can see that shock waves develop at the center of the cluster. They travel toward the outskirts. And in the central region, turbulence is also generated. This is instead a real observation of a cluster. The green now is the X-ray emission of the cluster, and the color is the radio emission. So this source here is the radio relic, and it traces particles accelerated at a shock wave similar to the one that we see here in the simulation. So now, what did LOFAR bring? What is the novelty that LOFAR brought into this field? So very briefly, what is LOFAR first? So LOFAR is a radio interferometer. The core is in the Netherlands, but then the antennas are spread all over Europe. LOFAR has two types of antennas, the LOFAR high band antennas operating between 120 and 240 megahertz, and the low band antennas operating between 10 and 90 megahertz. So LOFAR has really revolutionized the view of galaxy clusters, because now with LOFAR, we see every kind of interactions in the ICM. For example, we see radio galaxies or bubbles of old fossil plasma in the ICM interacting with shock waves, with turbulence, and being re-energized or re-accelerated by shock waves, for example. We also see tails of radio galaxies re-accelerated by gentle mechanisms, probably connected to turbulence, only visible at very low frequency. More recently, with LOFAR, we are also going beyond the scale of galaxy clusters, and we have discovered in two cases bridges of emission connecting pairs of pre-merging galaxy clusters. And connected to this fact that we are now able to go beyond the cluster scale, I would now start talking about radio megahalos. So here is just a picture to put you into context. So this is a simulation of the large-scale structure as would be visible in the X-rays in the future. And what we currently probe with the X-ray facilities is usually within R500. With in special cases with very deep X-ray observation, we are able to arrive up to R200, but this is only for a few clusters. In the radio band, we have radio halos that are usually well within R500. We have radio relics. As I said, radio relics are found at the outskirts of galaxy clusters. And in 2 cases, we have also seen bridges of emission connecting pairs of clusters. Now, in this cluster here, we have discovered that the central radio halo is surrounded by radio emission, low-far radio emission, that fills the entire volume of the cluster almost up to R200. This emission, the orange emission that you see here, is what we call megahalo. The scale of the megahalo is about 3 megaparsec. The volume occupied by the megahalo is about 30 times larger than the volume occupied by the radio halo at the center. The megahalo is not only much larger, but also it's much fainter with respect to the radio halo, and its emissivity is about 100 times below the emissivity, the typical emissivity of radio halos. Also, its surface brightness profile looks quite different. This is the surface brightness profile of the entire emission of this cluster. The central part, the radio halo, is can be well fitted with an exponential function, which is not peculiar of this cluster, but it's something that we do routinely do with most of the radio halos. However, the external part, what we call megahalo, is not only, of course, extending to much larger radii, but also the profile is much shallower. Now, when we discovered this megahalo, we wanted to understand whether this was a unique case in the universe and why. So we, together with the HERA Collaboration, I am also carrying out this project on a sample of clusters, a sample of 309 clusters selected from the Planck-Sunyaev-Zeldovich catalog. All of them have low-far observation at 140 megahertz, so low-far HBA observation. Now, I'm not going into any details of this sample because tomorrow there is a talk from a dedicated talk from Rossella Cassano. So I just wanted to introduce this sample because we used the images that we produced in the framework of the study of this sample to search for large-scale radio emission, larger than the typical scale of radio halos. And indeed, we found 3 more examples of megahalos in these 3 clusters that you see here. They all share similar characteristics. They all have a central radio halo at the center, and the megahalo is on a scale of about 2 to 3 megaparsec. In all the cases, it's the emission of the megahalo is much fainter, and the emissivity is well below the emissivity of the radio halo. And in all the cases, we see this discontinuity in the surface brightness profile. For 2 of these clusters, we also have low-far LBA observations at 50 megahertz. And unfortunately, for the Zwicky cluster, only the brightest part of the megahalo is visible. But for Abel 665, we are able to detect all the emission from the megahalo. The spectral index of these two megahalo is quite steep, so we are talking about a spectral index of about minus 1.6. And this may suggest that the emission, that the origin of the megahalo emission is connected to turbulence. Now, at this point, we wanted to understand why we see only 4 megahalos and why exactly in these 4 clusters. This is again the mass redshift distribution of the cluster of the sample that I mentioned before. And in this plot, we also derived these lines here, assuming not only that the surface brightness of megahalo goes down with redshift, but also that it increases with the mass of the cluster, because this is similar to what happens for radio halos. How the surface brightness increases with mass, we don't know. So here in this plot, we just assume 3 possibilities. The idea here is that with current low-far observations, we should be able to detect megahalos in this part of the diagram. Also here we have, in this part of the diagram on the left, with current observation, the possible megahalos would be resolved out. And in this left-hand part of the diagram, megahalos would be unresolved with the resolution that we currently need to be able to be sensitive to the emission of megahalos. It is interesting to see that the 4 megahalos that we detect actually lie in this part of the diagram. And there is also another star here, this is Abel 2255, where emission on much larger scale has been detected with very deep LOFAR observations. There are also other clusters in this region, they are labeled in gray. However, unfortunately, they have bad quality LOFAR data. So here, our idea is that with these 4 megahalos, we are just detecting the tip of the iceberg of a phenomenon that could be much more widely spread in galaxy clusters. And if we have deeper observations, we may be able to see many more megahalos. So for this reason, we are now carrying out an observational campaign with LOFAR. We already have some observation going on. We are, in particular, we are observing Abel 2218, which is one of the megahalos that I showed in LBA to have the spectral information. And also in LBA, we are observing Abel 2219, which is the most massive cluster of the sample. We could possibly observe another megahalo. And we also have HBA deep observation, 32 hours of Abel 2218. This will be very useful to study the detailed morphology of the megahalo and possibly discover some substructures in the emission of the megahalo. We are also planning to ask for other observations. In particular, we would like to have new HBA observations of the most massive clusters of the sample for those that have bad quality data at the moment, and maybe we could find new megahalos. So to conclude, we discovered very large scale, so 3 megaparsec scale diffuse emission in 4 massive clusters of the LOFAR sample that I only briefly mentioned, but I encourage you to follow Rossella's talk tomorrow. This emission we named megahalo, and megahalos have low emissivities, shallow profile, and steep spectrum. The origin of megahalo is still unknown. We have some ideas based on what we currently know. So if we look at the spectral index of megahalos, the spectral index is quite steep. So this suggests that the origin of megahalo is connected to turbulence processes. The fact that the surface brightness profile shows a discontinuity suggests that there is, at some radii in the cluster, something changes. What changes can be either a change in the macrophysical properties, so for example, what generates the turbulence in the 2 regions, but also it can be a change in the microphysics, so in the local properties of the plasma, or maybe in the particles, in the seed particles that are accelerated in the 2 regions. To gather more information and to answer some of these questions, now we have an ongoing LOFAR observational campaign. But in general, I think that megahalos are very interesting because they give us the possibility to probe the outskirts of galaxy clusters. The outskirts of clusters are a very intriguing and very interesting region because there is where all the accretion phenomena continuously take place. And they are, so far, they have been only probed in a few cases, and they are not even probed by current Xray facilities. And this is all from my side, and thank you.
Okay, that was the talk by Virginia Cuciti. I would like to thank all the speakers again. I suggest, by the way, that that questions for Virginia are asked on Slack or on GatherTown, because of course now we can collect all on GatherTown and continue our discussions there and meet each other. Thanks everyone, and see you there.